4.1, fundamental counting principle and permutations. The fundamental counting principle says if there are n ways to do one thing and m ways to do another thing, then there are n times m ways to do both things. And I know you've seen this before, and it's going to seem obvious sometimes, but let's look at an example. How many combinations are possible on this lock? So part A says without repeats, and part B says with repeats. So what you need to look at on this lock is notice that there are 4 different numbers, and you've probably seen one of these. You spin the little dial, and you've got numbers between 0 and 9, it looks like, for each of those 4 choices. Well, fundamental counting principle, I call like a blanks problem. And so since there are 4 digits on this lock, there are going to be 4 blanks in this blanks problem, in this fundamental counting principle problem. And so when it says without repeats, that's a little clue as to how this is going to work. So you look at the first digit, and you've got digits between 0 and 9, which is actually 10 choices. You've got 10 choices for whatever number is the first number on this lock. And then if they say without repeats, do you know how many choices you'd have on the second? There would be 9, because you can't repeat whatever the first one was. And then there'd be 8, because you couldn't repeat whatever the first 2 were. And then there'd be 7. So the answer is going to be 9, or 10 times 9 times 8 times 7. It's 5,040. So counting, we're not literally counting 1, 2, 3, 4, 5, because it would take us forever to count up to 5,040. So when we're talking about counting, we're talking about different kind of formulas and different techniques for figuring out how many ways there are of doing something. We're not literally going to count unless it's a tiny little number. We might count how many ways there are specifically, but I'm not counting 5,040 ways of changing those combinations on the lock. Okay. Part B says with repeats. So you can look at it the same way. You've still got 4 numbers to pick, but if I'm allowed to repeat, then that means 9999 is a possible combination. I'm allowed to repeat. So you still have 10 for the first, but you'd also have 10 for the second, third, and fourth. So the answer is going to be 10 to the 4th power, or 10,000. There are 10,000 ways of doing that lock. So we've got this concept of fundamental counting principle with repeats or without repeats. So number 2 looks like a lock you might have on your gym locker. How many combinations are possible without repeats? So on this one, it's a little bit harder to tell, but this last number here is 39. So we're going from 0 to 39. That means there are 40 different numbers possible on that lock. But you should know how a lock works. There are usually 3 numbers for a standard master lock like this. And so without repeats, you would have 40 numbers to choose from for the first number, and then 39, and then 38. 40 times 39 times 38. $59,280. Different combinations on that lock. Now, what about with repeats? Well, with repeats is easy by this time. You should be able to see that it's just going to be 40 times 40 times 40, 40 to the 3rd power, 64,000. Okay. Example 3. You've got some books on a bookshelf, and it says how many ways are there to arrange all 8 books on this bookshelf? So we're trying to arrange them or put them in order. I've got 1, 2, 3, 4, 5, 6, 7, 8. And if I want to arrange all 8 of them, it's like I have a blanks problem with 8 blanks. 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. 8 blanks. And so you can think about it this way. How many ways are there of choosing the first book to put in this position? Well, there are 8 books that I can choose from. All right. Now, once you've put this book down, how many ways are there of putting the second book down? There are only 7 books to choose from at this point. So it's kind of like the without repeats. You can't place the same book twice. And so then the third book and the fourth book and the fifth book, sixth book, seventh book, 8th book looks like that. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 happens to be 40,320. There are 40,320 ways of doing that. So how about part B says exactly 3 of the 8 books? This is a different question because we're only placing 3 books this time. We're not placing all 8 of them, so there would not be 8 blanks. There would only be 3 blanks this time. And so if you think about it, how many ways are there for me to pick that first book? 8. And then after I pick that first book, how many ways are there of picking the second book? 7. And then the third book, 6. It's like I'm just doing the first part of that last problem. 8 times 7 times 6 is 336. 336 ways of doing that. So this problem is a good example to show the next 2 definitions, a factorial and a permutation. A factorial is the number of ways to put a set of n items in order. So that's part A. That's what I did. And notice this notation in exclamation point. That exclamation point is a factorial. And you're going to see that on your calculator. You do want a calculator. You want a calculator with permutations and combinations and factorials. But you're going to see that. And the formula is this. N times n minus 1 times n minus 2 times, and you keep going until you get down to times 3 times 2 times 1. So essentially it does exactly what that problem A did. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is a factorial. So if you're looking at a calculator, you would type it in as 8 and then find the exclamation point. On mine, it's over there with the multiplication button. 8 factorial, 40,320. That's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, 0 factorial is weird. Okay, 0 factorial is weird, and it doesn't seem like it would make any sense. But 0 factorial is just defined as 1. So just memorize that. 0 factorial is 1. It should show you 0 factorial equals 1 on your calculator. That is just a definition. That is defined. That will always be the case. Now, if we're talking about a permutation, a permutation is the number of ways to put some subset of R items out of N items in order. And then it says you can think of a permutation as a partial factorial. A partial factorial. So if you're ever doing part of a factorial, that is a permutation. And the formula for that is n factorial over n minus r factorial. I'm not going to have you memorize that formula, but it's useful to know that's how it's calculated. So at some point, I'm going to ask you, is this a group from a larger group? We're taking a group of items out of a larger group of items. That's what we're doing. And putting them in order. This is exactly what we did in part B up above. We took 3 of those books out of a larger group of 8 of those books and put them in order. It was a part of a factorial because we just did 8 times 7 times 6. On a calculator, you can type that in. If you find the NPR function, and mine is above the division. And there are a couple of different ways you can enter it in depending on your calculator, but mine does this. 8 NPR 3 is 336. So try to find that option on your calculator. Those of you with graphing calculators, it'll be inside of your probability menu, or in your, you go to math and then over to PRB. So then number 4 is very straightforward. Evaluate P53. 5 NPR 3 is 60, and 4 factorial is 24. Now technically you should be able to do both of those by hand and without a calculator, but I'm using a calculator on that pretty much always. Okay, so the formula for permutation, if we were using the formula, it would say equals 5 factorial over 5 minus 3 factorial. And 5 factorial, that's 5 factorial over 2 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1, and 2 factorial is 2 times 1. And what ends up happening here is the 2 and the 1 cancel out, and you're left with just 5 times 4 times 3. 5 times 4 times 3 is 60. Now again, I'm probably never gonna have you do that by hand, but that's why it's happening. 4 factorial just means 4 times 3 times 2 times 1. So that's a lot easier to do by hand. That's 24. Number 5, consider the letters below, and it spells out thank you in Scrabble tiles. How many permutations of letters are there? Okay, so it says permutations. That's a little bit confusing, but permutations is just talking about putting it in order. Okay, how many different ways can we put those letters in order? So do I want to use all of them? Yeah, I guess so in this question. It's a little bit confusing language, but they're saying how many different ways of putting those things in order are there? Well, there are 7 of them, and we're putting them all in order. That's a factorial. If we're using all of them, it's a factorial. It's going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. 7. It's 8? Well, that's weird. How did I mess that up? Thank you. It is 8. 1, 2, 3, 4, 5, 6, 7, 8. 8. 8 factorial. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 8 factorial, which is 40,320. Now, one thing that's interesting, I think, is to recognize the relationship between a factorial and a permutation. I could do this using an NPR. It's just I'm going to put all 8 of them in order. So what that says is I'm going to take 8 items and put all 8 of them in order, and I get the same thing. Part B says how many ways are there to select 2 of the letters? Okay, and I think the language is a little bit confusing, so maybe it would be easier if I said order 2 of the letters, putting 2 of them in order. So out of the 8, I'm going to put 2 of them in order. That's a permutation. And so if you think about a permutation as being part of a factorial, it's easy to do this without a calculator, because I'm just going to take the first 2 parts of the factorial. The first 2 pieces of the factorial, this is going to be 56. So we can do that on a calculator. 8 NPR 2, 56, because I took the first 2 pieces of the factorial. Number 6, 8 runners are in a race. In how many ways could the runners place first, second, and third? First, second, and third. So you know, a lot of the times it's useful to ask yourself this question, because what gets tricky is you don't know if it's a fundamental counting principle problem or a permutation problem. And so sometimes you want it to be a blanks problem where there are 3 blanks. And you could do this problem as a 3 blanks question. All right. And that's probably the way I see this, is you've got first and second and third. I look at it as a blanks problem. And I can think about how many different ways are there for these runners to finish first. How many different people could finish first? 8, right? And then how many people could finish second? 7. And then 6 could finish third. That's going to be 8 times 7 times 6. That's 336. But here's the thing, and here's what gets super confusing later, is that might not be the best way of doing the problem. All right. So at some point, you're going to want to ask yourself, am I taking a group of items out of a larger group of items? Do you see how we're taking 3 out of 8 and putting them in order? It's probably going to be better for you at some point to notice that this is a permutation. You're taking 3 out of 8 and you're putting them in order. And whether you do 8 times 7 times 6, or you do 8 in PR3, either way, you're going to get 336. Okay. So I think what's super tricky is it's going to be easier for you to see 8 times 7 times 6 is 336. Don't fall into the trap of trying to make everything a blanks problem. Sometimes it's a blanks problem, sometimes it's not a blanks problem. Got to be really careful. Okay, next. A pet store currently has 4 dogs and 3 cats for sale. In how many ways can the pets be arranged in a row of 7 crates? All right, so 4 dogs, 3 cats, 7 crates. You can do this like a blanks problem. 1, 2, 3, 4, 5, 6, 7. Right. So it's a little bit confusing, I think, but there are no restrictions here. It doesn't say anything about what has to go where, which animal, whatever. So you've got 7 animals, and you're just trying to put the 7 animals in these crates. And so I've got 7 choices for something to put in that first crate. Might be a dog, cat, who cares? It doesn't matter. And then 6, and then 5, and then 4, and then 3, and then 2, and then 1. This is a factorial. 7 factorial. 5,040. But then they start putting restrictions on there. Part B says, well, what about if the dogs and cats are to be alternated? So you can't do it quite the same way. 7 crates, but you really have to think about how this works. So if I'm going to be alternated, that means it has to go cat, dog, cat, dog, cat, dog. But I don't think that's going to be possible. It has to start with the dog in order for this to work out and have 4 dogs. If you have 4 dogs and 3 cats, it has to be like that. Okay, it can't start with a cat. It's got to be dog, cat, dog, cat. In order to fill them up, 4 dogs, 3 cats. So if you think about this one, it's not quite the same problem as before, because there are not 7 different ways of filling that first crate. How many ways are there to fill that first crate? 4. And so if you just look at the dogs, 4 dogs, 3 dogs, 2 dogs, 1 dog, I kind of see a 4 factorial in there. But then we do the cats. How many different ways are there of filling in that second crate? 3 cats, very good, 2 cats, 1 cat. So you've kind of got a 4 factorial shuffled together with a 3 factorial. You've got 4 factorial, which is 24, and you've got 3 factorial, which is 3 times 2 times 1, that's 6. 24 times 6 is 144. That's a tricky question. You have to really read the language and try really hard to do exactly what it says. How about if all dogs are next to each other and all cats are next to each other? So that one's weird. That one's different, I suppose. All dogs are next to each other, and all cats are next to each other. So basically what they're saying is it has to go dog, 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 cat, 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 like that. Or cat, 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 dog, 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 dog. There's two different things that could possibly happen. Either they put the 4 dogs first, or they put the 3 cats first. One or the other, okay? And so something to remember, and I don't know if we've talked about this or not, but when you see the word or, a lot of the times it means we're going to add something. So learn that as quickly as you can. We've got something or something. Or is going to indicate that you're going to add two combination or two things. So if you want to do dog, 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 cat, 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 that's going to be 4 times 3 times 2 times 1 times 3 times 2 times 1. Well, that's 4 factorial, 3 factorial, which we just did a minute ago, which was 144. Or if I do cat, 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 dog, 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 isn't that just going to be 3 factorial times 4 factorial right there? Isn't that going to be another 144? We've got double the possibilities. 144 plus 144 is 288. Tricky stuff. Part D, in how many ways can 1 dog and 1 cat be selected? 1 dog and 1 cat. How many blanks are there? There are only 2 blanks in this problem. Typically when I see the word and, it's times. And is times, or is plus. But how many ways to select one of the dogs? Well, 4. How many ways to select one of the cats? 3. 4 times 3 is 12. None of those 4 problems is difficult. But what's hard is when you don't know which one's which. All right, so you really have to read and be careful with the language. The number of distinguishable, let me try this again. The number of distinguishable permutations of a set containing 2 or more indistinguishable elements is given by this formula. In factorial divided by. In 1 factorial. In 2 factorial. Dot, dot, dot. In R factorial. That formula looks really complicated and difficult. It's a lot easier to understand once you get into an example. I call this problem the Mississippi question. All right, the Mississippi question. You see the word Mississippi a lot when dealing with this type of problem. But let's look at number 8b first. Okay, example 8 says how many ways are there to arrange the letters of the word? And so I call this the Mississippi question because it's the most instructive example, I think. But if you look at Mississippi, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in the word. So basically we're arranging the letters, we're shuffling the letters. And if they were all different letters, all we would do is just shuffle them 11 ways to choose the first letter, 10 ways to choose the second letter, then 9, then 8, then so on, so on, so on. That's a factorial, okay? But because some of the letters are identical or indistinguishable, you could switch around a couple of those S's and I'd never know the difference, okay? If I'm trying to shuffle the letters and you just switch those 2 S's around or switch, shuffle the 4 S's, I'd never know. And so what this formula says to do is divide off the repeats, okay? So you're going to divide by, see how there's only 1 M? So 1 factorial. And see how there are 1, 2, 3, 4 I's? We're gonna do a 4 factorial. And that 4 factorial is how many ways to shuffle the I's, okay? There would be that many ways to just interchange the I's in position. See how there are 1, 2, 3, 4 S's? So we're going to do the same thing for the S's. And two P's, we're going to do the same thing for the two P's. Okay? So all we're doing is dividing off the number of ways of repeating or shuffling the individual letters. So we've got 11 factorial over all of that. Now, 1 factorial is just 1, so a lot of times people will just completely leave that off, and that's fine. But when you type that in on your calculator, you have to be very, very careful, and you have to do it the right way. And what I mean by that is you're probably going to need parentheses around that bottom. If you do not put parentheses around the bottom, then you should not expect to get that correct. All right, because your calculator doesn't understand what you're trying to do. It only knows the order of operations. So let's see if this works. If I do 11 factorial and I divide by parentheses, and I'm not typing in 1 factorial because I already know what that is. 4 factorial, 4 factorial, 2 factorial, close parentheses. Hopefully that works. 34,650. 34,650. I would highly recommend testing your calculator and make sure you can enter that in correctly. All right. Try it now. So number 8 says how many ways that are arranged the letters of the word orange. If I'm doing orange, I see 1, 2, 3, 4, 5, 6 letters. 6 letters. And if they're all different, it's just a factorial. If they're all different, we don't have to worry about indistinguishable elements because it doesn't apply. I guess if you did the indistinguishable elements formula, you divide by 1 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial, but you don't really need to. 6 factorial equals 720. So bookworm. Do I have any indistinguishable items in that? Yeah. So the formula comes into play. I've got 1, 2, 3, 4, 5, 6, 7, 8 total. So that's the numerator. And then look for repeats. See how you've got 1, 2, 3 O's? Do I have any other repeats? That's really all I need to divide by. All the others are just 1. You've got 8 factorial divided by 3 factorial. $67.20. Number 9. How many ways are there to line up the following playing cards? Okay. This is the exact same question. It's just a different way of writing it. Okay. So you've got a 7 and a 10 and an ace and a 5 and an 8 and an ace and an 8 and an ace and a 5. I just used the first letter of the word that I said, right? It's the same exact thing. You've got this nonsense gibberish word, but you've got some repeats. If they were all different, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. If they were all different, you'd have 9 factorial. But the fact that there are some repeats, you've got 3 aces that are identical and indistinguishable, and you've got a couple of 8s that are indistinguishable, and you've got a couple of 5s that are indistinguishable. The other 2 are just going to be 1s, so I don't need to do that. So 9 factorial over that stuff. Remember, when you type that in, you better use parentheses or else it's not going to be right. It's not going to do your order of operations correctly. $15,120. Counting means how many ways are there of doing whatever this is. Okay, there are 15,120 ways of shuffling those cards, basically. Number 10, student buys 3 Cokes, 2 Diet Cokes, and 2 Mountain Dews. She puts them in a refrigerator, planning to drink 1 a day for the next week. In how many ways can she arrange her drinks for the week? Think about it. Coke, 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 Diet, Diet, Mountain Dew, Mountain Dew. Those 3 Cokes are indistinguishable items. You can shuffle those 3 cans of Coke and you're not going to know which one's which. It doesn't matter. This is the same exact question. I think if you write it like letters like this and treat it like the Mississippi question, it makes a lot more sense. This is the Mississippi question. If all 7 of those things were different, it would just be a straight factorial, 7 factorial. But we have to divide off the number of ways of shuffling each of those 3 drinks. There'd be 3 factorial ways of shuffling the Coke cans, and 2 factorial ways of shuffling the diets, and 2 factorial ways of shuffling the Mountain Dews. 7 factorial divided by parentheses, 3 factorial, 2 factorial, 2 factorial. 210.